Hi there, Nick here, M0NTV, and welcome back to my shack and to another homebrew video. Right, thank you for those who watched the last video, which introduced the subject of the next building project that I'm going to be doing, which is to build another direct conversion receiver. And this one has an eye more towards people who are perhaps kind of towards the beginning of their amateur radio home brewing journey, and maybe folks that haven't had much opportunity to build radios from scratch. So I'm trying to keep it as simple as I can without compromising on the quality, obviously. But so with that in mind, we are going to start today, and we are starting observing that honoured ham radio home brewing tradition of when you build a radio, you start at the back end and you work forward. So we're going to start with the audio amplifier, and I'm going to show you first of all some that I've already built and tested and can confirm they work great a direct conversion receiver. So that will be fine. But if you, after I've talked through these things, you think, well, yeah, they're all right, none of these actually takes your fancy, hold fire, because later on in this video I've got something else up my sleeve which is much simpler, and particularly if you are just starting out, you might find that this is a bit more up your street and a bit more kind of manageable, but still does very well. So anyway, all of that is to come. Thank you for watching. I hope you find something of interest here, and as always, I hope you enjoy. And the first amplifier I'm going to show you is this one here. And this might look slightly familiar because this was the photograph of this was a screenshot for the last video. And if you watch the last video, you'll know I mentioned that half of this circuit I already had. This bit over here, that's an LM386 audio amplifier chip. I'd already got the audio amp. It was for a previous project that didn't come to fruition. But what I've added to it is this. Now this is an NE5534 audio preamp chip. And the design for this circuit is one I've used in just about every transceiver that I've built, and it comes from Charlie Morris ZL2 CTM, and I will link, as I have done in the past, but I'll link again to Charlie's schematic for that. It's pretty simple, really. I haven't even got a schematic, a printed schematic you can download for this LM386 circuit, just because there are so many available. The website I will link to is from circuitbasics.com, where Scott Campbell uploads a number of schematics for this chip. Very good, actually, and he walks you through it and kind of starts very basic and gets more complex, and how you can make a really pretty decent little audio amplifier with this one little chip. But if you pair this one little chip with the preamp chip as well, you've got quite a powerful little amplifier there, and that is more than capable of supplying all your volume needs for the direct conversion receiver and more besides. There's plenty of gain there. This is a voltage regulator because what I wanted to do was to run the Charlie Morris preamp on 12 volts, but actually the LM386 works better if you feed it 9 volts, I found. So I just knocked the 12 down to 9 with that voltage regulator. But yeah, so it's very good. So if you're interested in that, have a look at the Charlie Morris schematic. Have a look at that website that I will put in the description, and you can just basically stitch those two circuits together and do this. And this works fine. So, you know, why am I not just showing you this and getting on with another module in the radio? Well,
because I think, although this is fine, if you're particularly you're beginning, I mean, these little literal black boxes can be kind of, metaphorical black boxes as well, really. I mean, what's actually going on in there? It's hard to understand. We've got an input and an output and some biasing going on, but it's hard to see exactly what's happening. So you might prefer to build an amplifier that is made up of, instead of integrated circuits, with discrete components, i.e. transistors. And so that's what I'm going to show you next. Okay, number 2. And I've showed you this before. If you looked at my series on a direct conversion receiver last time, where I had the permeability tuned oscillator built on the glue stick, you'll see that I used this one. Then I built it for them, and this works well. This is a design by W8DIZ, Dieter Gentzow, and this was published in Sprat, Sprat 129, and Sprat is the official magazine of the GQRP club, and I would strongly advise, if you're not a member of that club, to join. It's very, very good value for money, and just a brilliant society to be a part of. Now, I will show you the schematic of this. Ignore this transformer. This was part of an experiment which I didn't use, so it's not actually in circuit. It's just hogging space on the board and confusing people. But essentially, it's just 4 separate transistors. 1, 2, 3, 4. But I will just show you the schematic of that now.
So here is Dieter's schematic, and essentially you'll see he's got a complementary pair here, 2N3904 NPN and 2N3906 PNP transistors together there, forming a kind of driver amplifier. And the main amplification is using, again, a complementary pair here. There's the 3904 and the 3906. This time working push-pull in a class AB amplifier. So that will give you more power, because basically each transistor's taking it in turns to do 1/2 of the waveform, essentially. Both class B, but biased a bit so you don't get the crossover distortion that you get if they were just purely class B. And that works great, and that will drive an 8 ohm load to your loudspeaker. And so that works brilliant, and I will link to this. This is just my LTSpice screen grab from Dieter's circuit, but that works fine, and you could build that. And I think you would do very well with that.
In a similar vein to Dieter's circuit is this one. And this is based on a circuit by, well, that living legend that is Mr. Pete Juliano, N6QW. And Pete's original design, I'll link to my, it's his circuit, but I've scribbled a few notes and things on it, but which I'll link to that. But in Pete's original design, he, like Dieter, had 2N3904 here and a 2N3906 here. But Pete contacted me actually when he knew I was building this and messing around with these circuits, and he said, try swapping out those 2 transistors, the 3904 and the 3906, and put in a tip 31C and a tip 32C, and they are the complementary transistors, but these are power transistors, audio power transistors, and he said you'll get a lot more juice out of it, and you don't need to change the biasing or anything, just swap them out. And I did, and he was absolutely right. It works great. And Pete's design is similar in that he has 2 two transistors here. Well, let me show you his schematic and you'll see.
So here is Pete's design, and you'll see he uses two 2N3904 transistors as two separate common emitter amplifiers, feeding then into this complementary pair in push-pull in class AB. And as I said, it works very, very similar to Dieter's, but gives you more volume just because these two transistors produce more power. And yes, so you could certainly use that, and that would work very well as well. Now, you'd think that giving you 3 different audio amplifiers would be enough, right? You'd think, wouldn't you? This is me, people. I just could not resist the temptation to have a go myself. So, if all those things are too complex, I have designed a simple audio amplifier, which consists of, the clue is in the title, just 2 transistors, two 2N3904 transistors. I'm going to just give you a quick sprint through the schematic now, and then we'll build it and test it, and you can see for yourself. It is very simple, but I think it is adequate to power my loudspeaker and to connect to my direct conversion receiver. Let me just say before we go any further, I am not an expert at all in any of this stuff. And I'm not saying that what I've produced is desperately the original. Of course it's not. I mean, I've come up with the biasing and stuff myself, but the designs are the designs that everybody uses, right? I'm not saying it's the best, that it's optimized, and you know, there are people watching this video, I'm sure, that could do something much better and more efficient and all the rest of it. All it is what I've come up with, okay? And I offer it to you, and particularly those that want something a bit simpler and want to be able to kind of understand what's going on a bit more easily. Hopefully you'll be able to do this with this design. Anyway, without any more further ado, let's get on with it. So here is my simple audio amplifier. Now, I think what I'm going to do is I'm going to produce a separate video on exactly how I designed this, how I came up with all these values for biasing, resistors, etc. and how I calculated the input and output impedance and all that business. But that's too much for this one video now. For now, I'm just going to take a very high level view and just point out a few things about it. The first thing to say about this circuit is it's actually 2 separate amplifiers joined together here via this 100 microfarad coupling capacitor. So ignore this second bit for a minute and just worry about the first bit. Just to say here, this voltage divider here, this is simulating a 5K potentiometer, which is our volume control, which is the only way you can really simulate it in LTSpice. I'm not going to run this as an LTSpice simulation, although that's what I did when I started. As I thought about it, I did it and put the values in as I calculated them. And the great thing about LTSpice is you can do some calculations then and see what it looks like. So this is the volume control, but essentially the signal comes in here. This first section is a common emitter amplifier. And so that will give us a fair bit of voltage gain and a fair bit of current gain, which is what we want. This second circuit is a common collector amplifier, otherwise known as an emitter follower. So this will have a very high input impedance, which is what you want, because you don't want to be loading down the previous circuit, and a low output impedance, which is what we want, because we want to be able to drive a low impedance load, a loudspeaker. And so essentially then the input impedance to this first stage is about 1,000 ohms, 1K. And the output impedance from the previous stage being the product detector via the Roy Llewellyn W7EL audio diplexer, will be about 50 ohms. So we've got 50 ohms coming from the product detector and an input impedance of about 1,000 ohms. That is good. Now, this is where you have to kind of make a mental shift here, because we're not in RF territory now where we have to match impedances. We're in audio territory, and in audio territory, generally speaking, you don't want to match impedances. What you want is the output of one stage to be much less, at least 10 times less than the input impedance of the next stage. That's the kind of rule of thumb, which we've more than got, because if we've got 50 ohms here, 500 ohms would be 10 times. Well, we've got nearly 1,000 ohms input impedance here, so that's fine. Now, obviously, when you adjust the potentiometer, the volume control, you are going to stuff up the input impedance. It will change. But it's not as bad as you think, because what you're in fact doing is whatever that figure of R1 is, will be in series with whatever the impedance, the input impedance of Q1 will be. And actually, I've calculated this. So the lowest it's going to be is like 950 ohms. And at the other end of the scale, it's much, much higher. So even, at the lowest level, we're well within our 10% ratio of the output impedance of the previous stage being a tenth of the impedance of the succeeding stage. So that's really good. So we'll get a good amount of voltage kind of showing up there. Now, the output impedance of this can get complex. So I'm not going to even go there really, but essentially this biasing resistor is being fully bypassed basically. So at DC, it's fine. It does what it's supposed to do and set the current. At AC, it's not going to impact the AC signal because I'm bypassing it here. But this resistor really is the one which sets the output impedance, because when you analyze this circuit from an AC point of view, where everything connected to a DC power supply is effectively at ground, and transistors are seen as current sources, and a current source with an infinite impedance. So essentially, from an AC point of view, the output impedance is this 620 ohm resistor in parallel with a practically infinite impedance. So, and as you know, if you put any two resistances in parallel with one another, the final total will be less than the lowest one, which in this case is it. So you won't be surprised to know that the output impedance is about 594 ohms with a 1 kilohertz signal. So let's call it 600, right? So we've got about 600 ohms coming out. Now, when you come into this stage, the input impedance is high, which, as I said, we want. And actually, probably more by luck than judgment, I have to confess, the input impedance is 6K. So 6,000 ohms. Well, that's absolutely perfect, because if we've got 600 ohms here, a factor of 10 higher is 6,000. So we've done the same again, right? So, this stage is 10 times smaller impedance than the input of this stage, which is what we want. And so what happens here is in this stage, we generate some current and some voltage gain. This stage will see no voltage gain at all. In fact, you get a slight voltage decrease. But that's all right, because this stage will preserve the voltage gains of the first stage, but what it will also do is ramp up the current so that at the output we get the same voltage gain basically as we got here, but much more current, which will enable us to drive that load, whether it's an 8 ohm load. I think I've got a 12 ohm speaker, which is why I've got 12 ohms in there. So that essentially is how it works. As I said, there are probably far better ways of doing it, but this is just what I came up with. And so we're going to try it out and see how we get on.
Now, one of the great things about designing audio circuits is that you can breadboard them before you even think about firing up the soldering iron. You can plug the components in here and see if it works or not, which is fantastic. It doesn't work so well for RF, of course, because all the stray capacitance and everything else, but for audio, yeah, fantastic. So let me just show you what I've got here. So I've got my little circuit here, and I've got it powered up here, 12 volts. You'll see it's drawing just 24 milliamps. I've got my phone, and my phone is set to the minimum volume that I can set it to, and that is feeding the input of the audio amplifier, and it's coming into this side of the potentiometer here. And then this little clip here, this lead, is taking the signal out, and that's then going into this loudspeaker here. Okay, so what I'm going to do is just put this down for a second, and hopefully you'll be able to see and hear what it sounds like. So I'm going to give it the old Johann Sebastian test, which is I like to play a little bit of Bach. So this is going to be Sheep May Safely Graze, and we'll see how this sounds. So I'm just turning the volume up now on this potentiometer. So if I crank it all the way up, there's a little bit of distortion there, so if I just kind of back it off a little bit. I mean, it's not hi-fi by any stretch of the imagination, but it's not bad, you know, and for 2 transistors, I mean, what do you expect? So, and I think for my purposes, in terms of the sound quality, you know, and the volume, that's going to be enough for me. So yeah, so I'm really quite amazed, really, that you can get that kind of sound from just 2 transistors pulling just 24 milliamps. So the next thing to do then will be to fire up the iron, and we'll convert this breadboarded circuit into something more permanent. So I'll see you at the bench. Welcome to the bench. And you see we've got the original circuit here on the breadboard, and what we're going to be doing is putting it onto here, onto a little bit of strip board, which is absolutely fine for audio, and it has the advantage that you can actually build things pretty small, which if you've seen any of my videos you'll know is a novel experience. So I'll take it when I can find it. So I haven't sold anything in yet, but I think what I'm thinking is having something a little bit like this, something a bit like this kind of arrangement, and So having the input in here controlled by the potentiometer and the output over here. Try and keep a bit of distance between the in and the out. And that should give me enough space here for all the transistors and all the biasing resistors and capacitors, etc. So that's what I think I'm going to go with. And the thing about building like this, I tend to just kind of do it as I go along, because I'm working off the schematics. I've printed out the schematic from my design, so I've got that, and I've obviously got the components there in front of me, and just take the time and build it up like that. So I'll show you what it looks like when I've got going a bit. Okay, so quick progress report. You see I've got the potentiometer on, I've got the input jack on, I've got the coupling capacitor on the input, and I've got the first two resistors of the first transistor's voltage divider. So what I've established here, because this port of the potentiometer needs to go to ground, I'm going to have ground, and this needs to go to ground. I can get this to focus a bit easier. That's better. And so perhaps I'll point, might be easier. And this needs to go to ground. I've got this. So this trace here, this top set of holes, is ground. And I've made this bottom set of holes the VCC, so the power, the DC power in. Now, so that simplifies matters when it comes to sorting some of this stuff out. Now you can see on here all these parallel tracks. So what you just need to be careful of is you need to get yourself one of these, a little kind of Breadboard device, which will make these holes that you can see. Because here, for instance, this is the coupling capacitor on the other side of this. So you need to spread it over 3 holes so that you can make a physical hole there. Otherwise, you're shorting out your capacitor. So you need to just have that in mind when you're placing these things. And actually, I find it a lot easier to make these physical breaks in the tracks as you go. Don't try and leave it to the end and remember, because you won't. You'll forget one, and you'll release the magic smoke, or it won't work, and then you'll finally think, oh yeah, I didn't make that hole. So I find it a lot easier to do these as you go along if you're going to build in this way. And actually, as you can see, the good thing about it is you can get those components in pretty tightly and save a fair bit of space. So we shouldn't have any worries, and because obviously we've got the associated circuitry here, but then we've just got this last one, and it's going to go on something like that. So we've got plenty of room there, which will be ideal. And I made sure that when I put this potentiometer on here, I put it right on the end, so that if I was to mount this in an enclosure, right, that's not going to be a problem. With this board is so light anyway, it will just hang off the wall of the enclosure. So there we go. So I'm going to crack on now. Oh, just to say, this big rather square block of blue tack, that's because I do actually have a PCB board holder, but what I tend to do, because I've got this, I took the decision, rightly or wrongly, to put the potentiometer on first. It doesn't sit easy, so I tend to kind of put a component in, like a resistor, bend the leads round, stick the holes through, put a small bit of blue tack across it just to hold it in place, and then go along with this big bit of blue tack here. I'll do it and then you'll see what I mean. And then you'll see like that, and that will hold it fairly firmly in place then as you're soldering your connections, and you just get the old snippers and make sure you get those off, and yeah, and that's how I go about it. Nice screaming hot soldering iron, and job's a good one. Right, so I will crack on and populate the rest of my circuit board. Just one other thought while I'm here. I've just put the first transistor in, there are different schools of thought as when it comes to soldering and temperatures and things. I mean, again, rightly or wrongly, it's just the way I do it. I'm of the school of having a screaming hot soldering iron, so the solder melts really quickly, and I don't have to have the iron on the legs of the component for very long. And I think that for me, that seems to work better. There's less chance of damaging the particularly semiconductors because the iron's not actually in contact with the leg for very long, because it doesn't need to be, because you've got enough heat going through there. So that's just one of my tips. Now, the other thing is make sure you've got a multimeter handy, because when you're taking resistors off and you've got a rat's nest like this, it's really, even if you think you know which one of those resistors it is, it's very easy to pick the wrong one and then solder the wrong one in the wrong place, you know. So what I do when I'm deconstructing a breadboarded circuit, like this one here, that's now loose, I've taken out, I will check it with the multimeter and sometimes double check it so that I'm sure I know which one that is, and then I can work out where it's going to go. So that's just another little tip when you've already got something built up and you're having to take it apart bit by bit to solder it up. Well, I'm pleased to say the bench is now clear, which means the amplifier is finished. Yeah, here it is. So yeah, quite pleased with that, really. It's quite a neat little job. Let's get it to focus, that'll be even better. And now, I think the only difference from the schematic was I added this 100 microfarad capacitor here, which is actually just sat across the DC power rail and the ground, and that's just a decoupling capacitor. So if any audio signal did happen to find its way onto the DC rail, it would be shorted to ground and wouldn't create any ripples going back into the DC chain. So that's just belt and braces, really. But actually, it turned out that little circuit board was just about the perfect size for this particular little circuit. So quite pleased. Now, what I ended up doing, you remember I said I had this track here was the ground, and this track here, the outside track here, is the DC power supply. When it came to actually feeding the cable in, of course, I didn't want to have wires stretching the whole thing. So I just used this little red wire here, which took the DC line coming in just to this empty track here, which is the second line across, which meant I could put the decoupling cap in and then feed it there, the 12 volts. And that was a bit more neater. So there it is. So now, of course, the only thing to do now is to take it back inside into the shack and give it the infamous smoke test where we power it up and really hope that nothing blows up or explodes or anything, and that it works at least as well as it did when it was in breadboard form. Okay, so here we are again. Got the JS Spark on here, all connected up again. Let's go. A little bit of distortion there, as there was before if you whack it up too high. But pretty good for 2 transistors. So yeah, really pleased with that. Now, one just word of warning, I think mine is 12 ohms, the impedance of that speaker. It'll work with an 8 ohm speaker. Don't try and be clever and connect it to a 4 ohm speaker, because you'll be disappointed, because it just won't produce enough current to drive a 4 ohm speaker. But 8 ohms, 12 ohms, if you've got something 16 ohms, something like that would be absolutely fine, I'm sure. And for my purposes, I think in this direct conversion receiver, that should be more than loud enough.
Now, clearly, there are all kinds of proper testing that I could have done on that amplifier that obviously I've not done, or at least I haven't showed you on the video that I've done. I've done a bit myself. But in the spirit of trying to keep things simple, I haven't bothered with all of that today. That partly because, as well, an audio amplifier, unlike just about any other part of a radio that you're going to build, is the one thing that you can do a fair amount of testing with no equipment at all other than your ears, right? Because that's the acid test, isn't it? What does it sound like? You can hear if it starts to distort. You can hear if you're overdriving the first stage. So it's something you can play around with yourself, and if you want to do some testing, if you build one yourself, absolutely fine. What I would say is have a look at some of these amplifiers. If you do try and build them, let me know how you get on. I'd be interested, but I'd be especially interested to know if anybody has a go at building my simple little one, what you reckon. And, whether you can make it work for you as well. I was amazed, really, at that volume level, really, with just 2 transistors. So, not hi-fi, a million miles away from hi-fi. But sometimes, the old GQRP club thing about sometimes it's folly to do with more what you can do with less. So if you can keep it simple, then that's a good thing. Thank you ever so much for watching this video. All power to you if you're going to have a go at building an audio amplifier for yourself. If you have enjoyed this video, please give it a like and do subscribe if you wish to follow the rest of this series and all my homebrewing adventures. Look after yourselves, and until the next time, bye-bye for now. 73.